All right, with this lesson, we're going to learn how to solve trigonometric equations. One of my favorite words, trigonometric. Often we just call them trig equations. What we're trying to do in these problems is to figure out the missing angle that would make true statements, that would make the equations I give you true. So, one of the most important things we need, along with our knowledge of our automatics and our trig basics, SOHCAHTOA stuff, are what's called Pythagorean identities. And we go back to this drawing of the unit circle. Remember, the unit circle has a radius of 1, as shown there, and centered at the origin. You can see the x and the y axes here. So here's angle theta. Relative to angle theta, the sine of angle theta is this opposite side over the hypotenuse. And what that means is, as we described in a different video, that the x-coordinate of this point is just the cosine. That tells you how far we go over, and the y-coordinate of that point is the cosine. So on this triangle, I want you to focus on this triangle right in here. These lengths are the same as the cosine of that angle, and the sine of the angle are the x and the y values, and the hypotenuse always stays 1. So from the Pythagorean theorem, we know that a squared plus b squared equals c squared, all right? And these sides are interchangeable in the Pythagorean theorem. So that's how we get this first Pythagorean identity. This side squared plus this side squared equals the hypotenuse squared. Sine squared theta plus cosine squared theta equals 1. So this notation, sine squared theta, means the same thing as the sine of theta all squared. Okay? But mathematicians, remember, I've told you many times, mathematicians are kind of lazy. We want to write as little as possible, and by agreeing that we could write it this way, we don't have to write the parentheses every time. All right? So, because the sine of theta squared without the parentheses would be a totally different thing. So if you're going to write it this way, you need the parentheses, but this way they said, okay, we'll let us write sine squared theta that way instead of the sine of theta all squared. Okay? So that's how we get this first one. Now, we can use that first one to get to the other two. Watch. Here's how we do it. So if we start with that first Pythagorean identity and you divide everything on both sides of this equation by the sine squared theta, divide everything by that, sine squared theta over sine squared theta is 1. Cosine squared theta over sine squared theta. Okay, well, knowing our laws of exponents, that would be the same thing as having the cosine of theta over the sine of theta and squaring the whole thing. When you have a fraction, okay, and you square the whole fraction, that squares the top and the bottom, so these would be equivalent. Well, cosine over sine is the same thing as the cotangent. Cosine squared over sine squared is the cotangent squared. And 1 divided by the sine squared, well, 1 over sine is the cosecant. So 1 over sine squared is the cosecant squared. That's where that second one comes from. I gotta back this out a little bit so you can see it all. Okay? And then, how we get to the third one is to start with this original one, and we divide everything by the cosine squared. All right? So if you divided everything up here in the original by the cosine squared, sine squared over cosine squared is just the tangent squared, because sine over cosine is tangent, so sine squared over cosine squared is tangent squared. Cosine squared divided by cosine squared of theta is 1. And 1 divided by the cosine squared theta, 1 over cosine is the secant, and so 1 over cosine squared is the secant squared theta. So those are the 3 trig identities that you're going to use to help us solve trig equations. Now you either have to memorize all 3, Or you can do what I do. I only memorize the one, and I know how to get to these other two, and I know my trig well enough that I can easily do that. Now, it might just be easier to memorize all three. Whatever, though, you got to know these three different trig identities, and you'll need to know them next year too, so don't put it off, okay? So those are the three. They're listed in your notes already. Now we got to learn how to use them. And I kind of forgot that I was going to use the back side of this, so we got to deal with those Sharpies coming through there. Maybe I can do them on a separate sheet of paper. Forgive me, I'm not going to start this over again. But when we get to, when we get down to this one, I'm going to rewrite it. Okay, so this first one, I'm going to zoom in now. Look at the directions. Solve for x. Find the angle x that if we plugged it in here would satisfy this equation. 2 times the cosine squared x equals -3 times the sine of x. All right, so here's the methodology. The first step is to try to transform this equation so you only have one trig function instead of two. We have cosine on this side, we have sine on that side. And we want to get it all in terms of just one trig function, not two. So we're going to use these Pythagorean identities to help us do that. And excuse me. This top one, the main one, has a relationship between cosine squared and sine squared. I could replace this cosine squared x with an expression that's equivalent to the cosine squared x. So what we're going to do, kind of an offshoot of this main one, I could solve this equation for the cosine squared x by subtracting the sine squared x, or theta in this case. In our equation it's x, but in the general one it's theta here. It doesn't matter, it's just a variable. So cosine squared of some angle is equal to 1 minus the sine squared of some angle. So I'm going to make this substitution. I'm going to replace the cosine squared x in this equation with 1 minus the sine squared x. Now there's a 2 that's out in front of that, so that has to stay there. So we're going to call this 2 times the quantity, 1 minus the sine squared x, equals -3 times the sine of x. Okay? So that's how we use the Pythagorean identity to get it all in terms of one trig function. Now I'm going to distribute this 2, and I get 2 minus 2 sine squared x equals -3 sine of x. And now it's just good old-fashioned algebra for a while here. Okay? So, after distributing that, now I want to get everything to one side of the equation, and I want to list these in decreasing powers of the sine of x. That sine of x now is our variable for a little while. So I'm going to move everything to the right because then my highest power of the sine of x will be positive, because this is a negative on the left side. If I move it to the right, it'll be positive 2 sine squared x. And then I've got a -3 sine of x. And then this 2 also has to be subtracted. And if I subtract 2, move it over there, I get this equation. 2 sine squared x minus 3 sine of x minus 2. That all equals 0. And now it's just like having an algebra expression. It's like having 2m squared minus 3m minus 2. See how that looks like this quadratic? Except instead of m, we have the sine of x. Okay? How would we approach that? We try to factor it if we could and solve. We're going to do the same thing here. We're going to factor this. Two is prime, so to get 2 sine squared x as a product, it's got to be 2 sine of x times 1 sine of x. And then we got to get some products here, 2 numbers that multiply to be -2, but also produce this right middle term here. And if I put the 2 there and the 1 there, 1 times 2 is 2. One of these has to be positive, one has to be negative to get a -2. And the middle term's got to be negative, so I'm going to make this negative and that positive. Okay? Now, I've got it factored. The next step, which I'll move up here to do this, would be to set each of those factors equal to 0 and solve. So the first factor, 2x, 2 times the sine of x plus 1, set that equal to 0, and then set the second factor equal to 0 also. Okay? And gotta back this out a little bit. There we go. Okay, so now here, 2 times the sine of x plus 1 equals 0. We're going to try to isolate the sine of x. So we'll subtract 1 from both sides, and we'll divide by 2. And we get the sine of x equals negative 1/2. All right, and now that's like doing that table. When in this range of values, remember we have a restriction here, x has to be between 0 and 2 pi. So we're just looking at the first revolution around the unit circle. What angles could we plug in for x in that first revolution of the unit circle that would give us the sine of that angle equals negative 1/2? Well, the sine is 1/2 in the 30-degree family, and it's negative in the third and fourth quadrants. Sine is only negative in the third and fourth quadrants. So we have to be looking at a 30-degree reference angle in quadrants 3 and 4. That's the information we can pick up there. That's the only time the sine is 1/2 is in the 30-degree family. And it's only negative, sine is negative in the third and fourth quadrants. The way this notation is here means we want the answers in radians, 0 to 2 pi radians. So I got to put this in terms of radians. So instead of 30 degrees, I'm going to think pi over 6 family. And pi over 6 family in the third quadrant is 7 pi over 6. That's the angle in that family in the third quadrant. And the fourth quadrant member of that family is 11 pi over 6. Okay? So these two answers come from this factor. The sine of x, the sine of either of these angles is negative 1/2. So these are answers for x. Now, we got to do the same thing with the other factor. But the sine of x minus 2 equals 0. When you add 2 to both sides, you get the sine of x equals 2. That never happens. The largest value we ever have for the sine of an angle is positive 1. That happens at 90 degrees. That's as tall as it ever gets. It's the highest the sine ever gets. So no solution will come from that. So our only answers for number 1 are 7 pi over 6 and 11 pi over 6. Okay? All right, I'll do one more, and then I'll end this video, and then I'm going to do the other ones that require a calculator on a separate video. Okay? So this one, 3 tangent to the third x minus the tangent of x equals 4 minus 3 secant squared x. Okay, first job, again, as it always will be, is to try to get this converted into an equation that only has one of the trig functions, not 2. So we got tangent and secant here. The trig identity that relates those two would be this third one. I know the secant squared is equivalent to tangent squared plus 1. I have the secant squared right there. Always look for the ones that are squared, because those are the ones that are equivalent, that show up in the Pythagorean identities, because we're using the Pythagorean theorem. So the secant squared right there is equivalent to the tangent squared plus 1. So I'm just going to make that substitution first. 3 tangent cubed x minus the tangent of x equals 4 minus 3 times the quantity tangent squared x plus 1. Then I'll distribute this negative 3, and we'll try to do some algebra for a while. Negative 3 times 1 is negative 3. Got to bounce that through, right? And now I'm going to move everything to one side of the equation and list these in decreasing powers of the tangent of x. That's cubed is the highest power. 3 tangent cubed x. This would be our next power. When I move that over, it becomes positive 3 tangent squared x. Then we've got this minus the tangent of x. That would be next. It's already on the left, so it doesn't change sign. And then 4 and a negative 3 is a positive 1 on the right side. When I subtract it, it becomes negative 1. So that would be my next step. Now, how are we going to factor this? Well, there's 4 terms, and there's nothing that's common to all 4 terms. This is a grouping problem. I could group, I have something common for those two. If I factor out a 3, the greatest common factor would be 3 tangent squared x for those 2 terms. If I factor out the 3 tangent squared x, I'm left with tangent of x and then plus 1. Now, both of these terms that are left over are negative, so I could factor out a negative 1, and that just makes it a tangent of x plus 1 inside there. And this is going to be successful because I have the same quantity showing up in the parentheses there. So if I go up here now, my next step would be to factor out the common factor, the tangent x plus 1. If you factor those out, imagine those being crossed out. Whatever's left is your other factor, 3 tangent squared x minus 1. And there is our factorization. Now, we set these factors equal to 0 and we solve. Well, setting this one equal to 0 and solving, I just subtract the 1 from both sides. I get tangent of x equals negative 1. That's easy enough. This one's a little trickier. If I set this equal to 0 and solve, I'm going to save some steps here. I'm going to add 1 and divide by 3. I get the tangent squared x equals 1/3. Okay? If I add 1, divide by 3, I get tangent squared x equals 1/3. This one's ready to go. Let's do this one. When is the tangent of x equal to negative 1 in that first revolution of the unit circle? Well, the tangent is 1 in the 45-degree family, or pi over 4 family. And it's negative, the tangent is negative only in the second and fourth quadrants. So the second quadrant pi over 4 family is 3 pi over 4. And the fourth quadrant is the other quadrant when the tangent's negative, and pi over 4 family there is 7 pi over 4. Okay, so those angles come from this factor. This one, we got one more step. We have to get the tangent of x by itself. We got to take the square root of both sides, and we got to make sure that we do plus or minus. Tangent of x equals plus or minus the square root of 1/3, which would be 1 over the square root of 3, or square root of 3 over 3 when I rationalize that. Okay? So, when is the tangent of x equal to a positive or negative square root of 3 over 3? Well, the square root of 3 over 3 occurs in the 30-degree family, or pi over 6 family. And the fact that it's positive or negative here, which is important whenever you take the square root of both sides, plus or minus the square root of that, positive negative means it could be all 4 quadrants. So it's the pi over 6 family, all 4 quadrants. So pi over 6, first quadrant. The second quadrant is 5 pi over 6. The third quadrant is 7 pi over 6. And the fourth quadrant is 11 pi over 6. This particular equation has 6 different answers. And what this means is if you plugged in any of these angles and your final answers in place of x in the original equation, both sides would turn out to be the same. Same thing here.